Hello, hi again, everybody. So now we will continue our discussion in topic 6 with the second method in the optimization, that is the simplex method. All right, the simplex method that we're discussing now is predicated on the assumption that the optimal solution will be at an extreme point. Thus, the approach must be able to distinguish whether during problem solution an extreme point occurs or not. To do this, the constraint equations are formulated as equalities by introducing what we call as slack variables. This slack variable measures how much of a constraint resource is available. That is, how much slack of the resource is available. Okay. For example, recall the resource constraint used in example 1 and example 2. So we have 7x1 plus 7x2, plus 11x2 lesser than 77. We can define a slack variable S1 as the amount of raw gas that is not used for a particular production level, which is x1 and x2. If this quantity of a slack variable S1 is added to the left side on the constraint, it will make the relationship to be this one, like 7x1 plus 11x2 plus S1 equal to 77. Now, recognize what the slack variable can tell us. So if the slack variable is positive, it means that we have some slack for this constraint. That is, we have some surplus resource that is not being fully utilized. If the slack is negative, it tells us that we have exceeded the constraint. Okay, that is negative. And finally, if it's 0, that we exactly meet the constraint. So that means we have used up all the allowable resources. Since this is exactly the condition where constraint lines intersect, okay, so the slack variable provides a means to detect the extreme points. Now, a different slack variable is developed for each constraint equation, resulting in what is called as the fully augmented version. Okay, so we have here maximum Z equal to 150x1 plus 175x2, which subject to the constraint A, 7x1 plus 11x2 plus S1 equal to 77, B, 10x1 plus 8x2 equal plus S2 equal to 80, and then constraint C, x1 plus S3 equal to 9, constraint D, x2 plus S4 equal to 6, and the positivity constraint, which is x1, x2, S1, S2, S3, S4 must all greater than 0. Notice how we have set up the 4 equality equations so that the unknown are aligned in columns. So we did this to underscore that we are now dealing with a system of linear algebraic equations. Okay. In the following section, showing these equations can be used to determine extreme points algebraically. The example system from the previous slide, or the set of equations that we discussed in the previous slide, is underspecified and undetermined because it has more unknowns than the equations. So in general terms, there are n structural variables that is come from the original unknowns, and then there are m surplus or slack variables. It's 1 per constraint, and then 1 plus m total variables. That is the structural plus surplus variables. For our example, or for the gas production problem, we have two structural variables here. If you can see, the x1 and x2, and then 4 slack variables, s1 to s4. So making the total of 6 total variables. Alright. Thus, the problem involves solving 4 equations with 6 unknowns. The difference between the number of unknowns and the number of equations, which is 6 minus 4 in our problem, equal to 2, is directly related to how we can distinguish a feasible extreme point. So specifically, every feasible point has 2 variables equal to 0. So we must have 2 variables out of 6 variables that equal to 0. For example, the 5 corner points of the area from the graphical depiction of the problem, you can see from figure 9 in the lecture notes. The area of A, B, C, D, E have the following 0 values. So like for the point A, we have x1 and x2 equal to 0. For point B, we have x2 and s2 equal to 0. C, s1 and s2. D, s1 and s4. E, x1 and s4 equal to 0. This observation leads to the conclusion that the extreme points can be determined from the standard form by setting 2 of the variables equal to 0. So in our example, this reduced the problem to a solvable form of 4 equations with 4 unknowns. So when you have 4 unknowns, then you can solve using 4 equations. For example, for point E, so referring to the table here, setting x1 and s4 equal to 0 can reduce the standard form into this. So from the standard form previously, it can be reduced to the 11x2 plus s1 equal to 77, and 8x2 plus s2 equal to 80, s3 equal to 9, and x2 equal to 6, which can be solved for x2 equal to 6, s1 equal to 11, s2 equal to 32, and s3 equal to 9. Together with x1 and s4 equal to 0, so these values define the location of point E. In general, a basic solution for m linear equations with n unknowns is developed by setting n minus m variables equal to 0 and then solving the m equations for the m remaining unknowns. For example, in our discussion previously, so we have 4 linear equations and 6 unknowns. And then to have the basic solution, we have to develop by setting n minus m variable to 0. So we need to set 6 minus 4 equal to 2. So 2, we must setting 2 variables that equal to 0. So from previous example, we have point E where x1 and s4 equal to 0. That is two variables setting to 0. Okay. And then solving the m equations for the m remaining unknowns. Since we have two 0 variables, so the remaining is 4. The remaining is 4 variables. Okay. Then it can be solved because we have 4 linear equations. The 0 variables are formally referred to as non-basic variables, whereas the remaining m variables are called as basic variables. So for example, previously, point A, we have x1 equal to 0 and s4 equal to 0. So this is called as 0 variables, and also formally referred as non-basic variables. Whereas the remaining, okay, since we have 6 total variables, the remaining is x2, s1, s2, s3. Okay, the remaining is 4 lah, 4 variables. Okay, considered as basic variables. Okay, if all the basic variables, which is this one, are non-negative, that means not equal to 0, so the result is called as basic feasible solution. So this is where the optimum points. Okay. Now, a direct approach to determine the optimal solution would be to calculate the basic solutions and then to determine which were feasible, and among those, which had the highest value of Z. So there are two reasons why this is not a wise approach, which is not so good. The approach can involve solving a great number of equations. So like for m equation, with n unknowns, this results in solving Cm power of n equal to n factorial divided by m factorial times by n minus m factorial simultaneous equations. So for example, if there are 10 equations, which is m equal to 10, with 16 of unknowns, that means n equal to 16, you would have 8008 10 times 10 systems of equations to solve. That means you need to solve numerous number of equations. And then the second one, a significant portion of this may be infeasible. So for example, in the presence of problem, out of C6 power of 4 equal to 15 extreme points, okay, only 5 are feasible. So clearly, if we could avoid solving all these unnecessary systems, a more efficient algorithm would be developed. Let us look at how to implement the simplex method. So this method is described in example 5. Okay, the simplex method avoids inefficiencies outlined in the previous section. It does this by starting with the basic feasible solution Then it moves through a sequence of other basic feasible solutions that is successively improve the value of the objective function. So the objective is to improve the objective function. Eventually, when the optimal value is reached, and the method will be terminated. So once the optimal value is obtained, the method will be terminated. Okay, for example 5, okay, implementation of simplex method, we will illustrate the approach using the gas processing problem in example 1 and example 3. The first step is to start at a basic feasible solution that is at an extreme corner point of the feasible space. So here we have like 6 feasible point, which is A, B, C, D, E, and F. Okay. For cases like ours, an obvious starting point would be at point A. So here in the red circle. That is, at point A, x1 and x2 equal to 0. So this is the non-basic variables, or the zero variables. The original 6 equations with 4 unknowns will become all this once you substitute the value of x1 and x2 that equal to 0. Thus, the starting values for the basic variables, so all these are the basic variables, are given automatically as being equal to the right hand side of the equations. Okay, so we get the value for all the basic variables automatically from the process. Okay, before proceeding to the next step, the beginning information can now be summarized in a convenient tabular format called a tableau. So as shown here, the tableau provides a concise summary of the key information constituting the linear programming problem. Notice that for the purpose of the tableau, the objective function is expressed as z minus 150x1 minus 175x2 minus 0s1 minus 0s2 minus 0s3 minus 0s4 equal to 0. So that is as in the first row. Okay. And so the other rows consists of the constraints equation here. The next steps involve moving to a new basic feasible solution that leads to an improvement of the objective function. So we need a better objective function. So this is accomplished by increasing the current non-basic variables, which is at this point is x1 or x2. So x1 or x2 here above 0, so that z can be increased. Okay. Recall that for the present example, extreme points must have 2 zero values. Okay, therefore, one of the current basic variables, which is S1, S2, S3 or S4, must also be set to 0. So you need to know how to differentiate what is the non-basic variable and the basic variables. Okay. To summarize this important step, one of the current non-basic variables must be made as a basic variable, which is a zero variable made to be non-zero variable. So this is called as entering variables. And then, meanwhile, in the process, one of the current basic variable must be made to non-basic variable, which is from non-zero variable made to be zero variable. So this is called as leaving variable. Now, let us develop a mathematical approach for choosing the entering and leaving variables. Okay, because of the convention by which the objective function is written, the entering variable can be any variable in the objective function having a negative coefficient. So we can check here, entering variable can be any variable having a negative coefficient from this objective function. So you can check which one is the negative, which one is having a negative coefficient, because this will make the z bigger. Okay. So the variable with the largest negative value is conventionally chosen because it usually leads to the largest increase in z. Okay, so if we check for the largest negative value between the coefficient for x1 and x2, so the coefficient of x2 is bigger because it has negative 175 compared to negative 50 for the x1 coefficient. So recall that before this, the non-basic variable, which is the zero variable, consists of x1 and x2. So for this step, we need to change one of the non-basic variable into basic variable, which is non-zero variable. So for this one, for our case here, we choose x2 because the coefficient is negative 175. Okay? Okay, at this point, the graphical solution can be consulted for insight. As in figure shown here, we start the initial point at A. Okay, based on its coefficient previously that had been discussed, x2 should be chosen to enter because x2 has the higher negative coefficient, which is 100 negative 75. But to keep the present example brief, we choose x1, the second higher coefficient, negative coefficient, because we can see from the graph here that this will bring us to the maximum quicker, which is C is the maximum. Okay, as we can see here, from A to B and then B to C is quicker compared to from A to E and then E to D and then D to C. Next, we must choose the leaving variable from among the current basic variables, which is S1, S2, S3, and S4. Graphically, we can see that there are two possibilities, which is moving to point B will drive S2 to 0, here, point B, whereas moving to point F will drive S1 0. But the graph also make it clear that F is not possible because it lies outside the feasible region here. Okay, thus we decide to move from A to B. How is the same result detected mathematically? One way is to calculate the ratio of the right-hand side of the constraint, which is the solution column from the tableau, to the entering variable of x1. So for example, for the first constraint select variable of s1, The result is 77 divided by 7 equal to 11. And then the remaining intercepts can be calculated and listed as the last column of the tableau. Because 8 is the smallest positive intercept, it means that the second constraint line will be reached first as x1 is increased. So this line. Hence, S2 should be the living variable. At this point, we have moved to point B, where x2 and S2 equal to 0. And the new basic solutions become these new constraint equations. Okay. The solution of these equations effectively define the values of the basic variables at point B. So we get x1 equal to 8, s1 equal to 21, s3 equal to 1, and s4 equal to 6. The tableau can be used to make the same calculation by employing the Gauss-Jordan method. For this example, referring to the first tableau from the previous slides, the pivot row is S2, which is the living variable, and the pivot element is 10, which is the coefficient of the entering variable x1. So dividing the row by 10, which is this row in the first tableau, and replacing S2 by x1, so this is where originally S2, will give the new set of tableau as shown here. Alright, this is the second tableau. Okay, next, the x1 coefficients in the other rows can be eliminated. For example, for the objective function row here, from the tableau, the pivot row is multiplied by negative 150 because the coefficient of x1 in the pivot row is negative 150. And the result subtracted from the first row to give this answer. So that means the process is first objective function row minus with pivot row multiplied by negative 150. Similar operations can be performed on the remaining rows to give the new tableau, which is the third tableau. So the new tableau summarizes all the information for point B. This includes that the fact the move has increased the objective function to z equal to 1200. The tableau can be used to chart our next step, or in this case, in our case, example 5, it is the final step. So if we see here, only one more variable, which is x2, has a negative value in the objective function, and it is therefore chosen as the entering variable. According to the intercept values, here the last column, now that calculated as the solution column divided by the coefficient in the x2 column, because x2 is the entering variable. Okay, so the first constraint has the smallest positive value, and therefore S1 is selected because selected as the living variable. S1 is selected as the living variable because the intercept is the smallest positive compared to the other values. Thus, the Simplex method move from B to C. So now we are at point C, okay, as mentioned before. Finally, the Gauss-Jordan elimination can be implemented to solve the simultaneous equation. We're using Gauss-Jordan elimination. And the result is the final tableau here. How we know that the result is the final? Because there are no negative coefficients remaining in the objective function row. As you can see here, there are no negative coefficients. So that means our result is the final. And the final solution is tabulated as x1 equal to 4.889, x2 equal to 3.889, and the maximum z is 1413.889. Then, since S3 and S4 are still in the basis, we know that the solution is limited by only the first and second constraints. So that's all for the example 5.